these notes are going to go over 14.6, which is reaction mechanisms. Okay, so you should have your notes packet out. So at the very beginning, before Thanksgiving, we defined a reaction mechanism. It's the step-by-step view or the step-by-step path from reactants to products. Most reactions are not one step. There are things that happen in between. And so here is a diagram of an organic reaction. Obviously nothing we're going to do in AP Chem, but here's your reactant and this is your product. And in between, to go from here to here, there are a lot of steps that happen. There are 4 steps that happen. And so a reaction mechanism just goes through those steps. And so in a reaction mechanism, each step is called an elementary step or an elementary reaction. If the step or the elementary step only has one molecule as a reactant, it is known as unimolecular. If that step has 2 reactants as molecules, it is bimolecular. Termomolecular reactions are not very common, but that would be you had 3 molecules or 3 particles as your reactant. So looking at this 2-step mechanism. So this is a reaction where you're going to start off with NO2 and we make CO2. And so this has 2 steps. This step right here has 2 reactants. This step has 2 reactants, so these are both bimolecular. Now, question B says, what is the actual reaction? And so when you look at a mechanism, as I showed earlier, there are lots of steps, and a lot of times there are things that are involved in the reaction that actually aren't a product. And so when I look at this mechanism, there's NO3 that's produced in step 1, but then it gets used up in step 2. It's not actually one of our products. So this is not a part of the actual overall reaction. It's involved in the reaction, but it's not a product, and it's actually not one of our original reactants. And then looking else at this reaction, we can see that we have 2 NO2s that we start out with, and then we produce 1 NO2. So that we can also cross off. And so you can, when you look at reaction mechanisms, if something is on the left side and then it's on the right side of the arrow, you can scratch it out. It's not a part of the overall reaction. And so our overall reaction is actually, we've got NO2, and then we also have CO as a reactant. And that will produce this and this. And so that's what you would see, when you're looking at a normal equation, but really carbon monoxide doesn't come into play until the 2nd step. It is not involved in this 1st step at all. Okay. Part B we just did. So C said NO3, as we talked about, it's not a reactant and it's also not a product. It's formed here and gets used up here. This is an example of an intermediate. That's what we call things like that. So, an intermediate, not mediated. So, an intermediate is something that is formed in one step, and then it's just used in a later step. Okay. Flipping over. Yesterday we looked at energy diagrams for reactions. That was for an overall reaction. Knowing that reactions have steps, their energy diagrams sometimes can look like this, and they can actually look a little bit crazier. And so if we look at what's going on, here was my original reactant, and this is my actual product. And B right here represents an intermediate. So we have some type of intermediate being formed. And so you can look and see that A, to get this reaction going, it has to meet a certain activation energy. The first step will happen. So once it hits here, our first step goes, and then we make an intermediate right here, and then this would be, after B, to get to C, the second step. And hopefully you notice there's another little hill. So there's another activation energy that has to be met before the reactant is formed. So if I were to label this, step 1 is like from A to B, and then step 2 is from B to C. Now, something important that the notes point out, intermediates are not the same as transition states. Transition states we talked about yesterday is where like half the bonds are broken, half the bonds are formed. Intermediates are actually sometimes, not always, but stable things. They are not, a halfway reactant, a halfway product. They are usually something different. Transition states, or the activated complex, is really what we called it yesterday. Activated complex, they're unstable. You can't isolate them because it's half a reactant, half a product. Here is just another probably nicer view, if you want to stop and sketch that one, of a reaction, a two-step reaction pathway. And so again, there are two activation energies that need to be met. The one for step 1, and then they can make the intermediate, and then another one to make your final product. So here we have another example of a two-step reaction. And so looking at this, it wants to know what the MoCO5 is classified as. Well, if I look at this reaction, I see it right here, and then I see it on the left side of the equation. So this is known as an intermediate. It gets made, and then it gets used. And then my CO, what would just my carbon monoxide be? I see it over here, and I don't see it anywhere else. So if it only appears on the right side of the equation, it's a product. It's not included in step 2 because it's not used in step 2, but that doesn't mean that it's not a product still. Okay, and so looking at this, this little paragraph is important. So we talked about earlier that rate laws have to be determined from experimental data. You can't figure out the order of a reaction by just looking at coefficients. That's not possible. However, we can figure out the rate law by looking at the elementary steps, which just means the steps of the reaction mechanism. And then you would have to confirm with experiments that that rate law was correct, but you can, for the most part, figure out rate laws based off of looking at the steps. And so the rate law of any step, remember elementary step is just any step in a reaction, step 1, step 2, step 3, it's based on its molecularity. And so what that means is if you have a unimolecular step, that it is a first order. And if you have a bimolecular step, it is going to be second order. And really fast, in case you forgot what a unimolecular step is, unimolecular is when they have one reactant. Bimolecular, there are two reactants. And termolecular, honestly, we're not going to talk about, like ever, because they are really, really rare. And so a unimolecular reaction, what it looks like, again, you have something and it makes a product. And unimolecular is going to be a first order reaction. So the rate for that step, now I'm saying that step, not the entire reaction, is Ka. An example of that would be N2O4 will break down into this. That's a unimolecular step, just one reactant. Bimolecular step, you have two reactants. It could be you have A plus A, and then you make a product, or we have A plus B, and we make a product. but bimolecular steps are second order, and so your rate could be Ka squared, or for this case, it would be rate equals Ka B. An example, 2NOCl makes 2NO plus CO2. And right now, I can already tell you might want to pause this video, sorry, and go back in your notes, because I know I already messed up, and when I said it, I thought it was wrong, which is probably why it sounded funny. This is not a unimolecular step, that is bimolecular, just like this shows. And then a termolecular step would just be you have 3 reactants and you make a product, or it could be like ABC or whatever. And we're not going to talk about this. Okay. And so reaction mechanisms are going to be 2 or more steps. Each step has its own rate, as we just said. And because it has its own rate, it's going to have its own rate constant, and they have their own activation energies, which is why on the graph, step 1 has this activation energy, step 2 has this activation energy. And usually, one step is going to be much slower than all of the others. Now, the overall reaction rate can't be any faster than the slowest step. You know, like in class when you're doing notes, the pace of the class can't go any faster than the slowest writer. Same thing. Or if you look at this little picture pouring water into funnels, it doesn't matter where the smallest funnel is. If it's first, if it's second, if it's third, the smallest funnel is what's going to determine how fast the water can go into the flask. Because, you know, it gets stopped up, it can't go through the small funnels as fast. And so the slow step of a reaction mechanism limits the reaction rate, and that is called the rate determining step. And it's based off of the slow one. And so looking at this mechanism, it is the same one we saw before. I'm telling you this step 1 is the slow step. So that is our rate determining step. That is the one that's going to determine the reaction rate. And so H asks us to write the balanced equation. We did that earlier for this one, but in case you forgot, that gets used up, choo choo. So our balanced equation would be NO2 plus CO. And whenever you're looking at reaction mechanisms, make sure you go through each of the steps and write all your reactants. And then NO plus CO2. So that's my overall reaction. And then the rate law for this reaction is going to be based on the rate determining step. And when I go to my rate determining step, the slow one, it is bimolecular, which means it's going to be second order. So rate equals K times NO2 squared. The rate is based off of the slow step. Now, reactions mechanisms can't be proved. You know, we're talking about atoms and molecules here. Can't go take a screenshot of it and prove that it happens. And so rate laws have to be, you can predict them, but they do have to, for it to be true, it does have to be consistent with experimental data. So you do need to have data to back up a rate law. We're going to look at a few more reactions, write them, and talk about their rates, because it's not always as easy as that one. So here we have a two-step mechanism again, and it has a slow initial step. So this is my rate determining step. You might want to label that. You don't have to. I like to. And J asks us to write a balanced equation. Okay, well if I look at what's going on, I've got N2O on the left, and then down here it's on the left, so that's not an intermediate because it's on the left side both times. N2 is on the right, and it's on the right, not an intermediate. And then I've got oxygen on the right, and then oxygen on the left. So that is an intermediate. And then O2 as a product. So my only reactant that's left over is N2, and I have N2 twice. So 2, N2, and I was saying N2, I meant N2O. And then let's underline, we marked those. And then I've got this as a product, there are 2 of them, so 2 N2, and then plus my O2. Notice, even if the equation is balanced, is it balanced? Yes, it is. So even if you forget to include both of these N2Os, you would have to add a 2 here anyway to balance it. So just always make sure that your equations are balanced. And then we're going to write the rate law. So the rate law comes from the rate determining step, which is the slow step, and that slow step is unimolecular. There's only one reactant, so rate equals K times N2O. And it's first order, unimolecular first, uni first, by 2. Now we're going to look at a reaction that has a slow second step. And so the fast step happens really fast, and looking at this, the arrow forward and the arrow backwards means that that's a reversible step. And then this is telling us that K1 and then K negative 1. K is your rate constant. And so with this labeled, you can kind of deduce that the rate constant for the forward and the rate constant for the reverse are the same. Now, we'll talk about that in a few minutes. Let's just look at the rest of it. And then we have K2 down here. So this is going to be a different rate constant for step 2. And step 2 is looking like it's not reversible because there's not another arrow. When I look at this reaction, I do notice that NOBr2 is an intermediate. It gets used up. Okay, so K says since step 2 is our rate determining this step, the rate law for that one governs the rate of the overall reaction. And so we're going to write the rate law based on step 2. Now, just because it is an intermediate, we still have to include it when we write the rate law. So K, NOBr2, and then NO. That is what it would look like. Now, you have to write it. That does not mean it's correct. And we're going to talk about how to get a correct rate law. Intermediates, they are usually unstable, not always, and they can have low unknown concentrations, but they're not a part of the final product. And so you cannot have a final answer rate law with an intermediate in it. But you can't just take out the intermediate and make it NO2 squared, because I can tell you right now that's not going to be consistent with your experimental data. And so instead we need to look at the other parts of the reaction to figure this out. But you can't have an intermediate in your final rate law. You also can't just not write the intermediate. That doesn't work either. And so this first one, it told us it was a fast and it's a reversible process. And so we can say for that fast reaction, that is bimolecular, that this is the rate of the forward. It would equal the rate of the reverse. And we know this is true because the rate of the forward reaction equals the rate of the reverse reaction. Because it is a very fast, reversible process. You can't say that for a slow, but we're going to assume that with this one. That is an assumption you can make. If it's the first step and it's fast and it's reversible, that the rate of the first forward equals the rate of the reverse. And so now we have two equations that we can use. We have the one we wrote up above, so rate equals K NOBR2 times NO. And then we have this reaction 2. And so I'm actually going to rework this one to get NOBR2 isolated, and I want to isolate that because that's my intermediate. And so really fast, my K1 NOBR2 equals K -1. I just write -1, so I remember it's the reverse, NOBR2. And so again, why are we doing this? Because this can't be our overall rate law. That can't be your final answer because that's an intermediate. And so we went to the first step again, which is this, and we said because it's fast and because it's reversible, the rate of the forward equals the rate of the reverse. And now, because I'm trying to change this reaction into something proper that we can say, I'm actually going to solve for NOBR2 and isolate that variable. And so to get this by itself, I'm going to actually divide each side by K to the -1. So now that's gone, and now we have NOBR2 equals K1 times NO times BR2 over K to the -1. And now I have something that my intermediate equals. And so my original bad rate law, I'm going to substitute NOBR2 equals all of this. So I'm going to plug this into that equation. So I have rate equals K, and then instead of writing NOBR2, I'm going to write what we said it equals, which is right here. And again, we got this from the first step. So K1 times NO, and that should be a bracket, BR2 over K to the -1. And then what was the rest of my equation? The rest of it was NO. And now we have a rate law that doesn't have any intermediates in it. Now this rate law isn't perfect. We do need to simplify it a little bit. And so we've got, whenever these numbers we said earlier, they're fast, they're reversible, they're going to equal one another. We can scratch those out, those rate constants. And so now we have rate equals K times NO, and again that should be a bracket, times BR2 bracket times NO bracket. Now hopefully you can see these are both NOs, so we should combine them. And so our final answer is going to be rate equals K NO squared times BR2. And that would be our final rate law that doesn't have any intermediates inside of it. And so this is on the very back of this page. But in general, when you have a fast step before a slow step, you can solve for your intermediate by assuming that there's an equilibrium. So assume that reverse and forward equal each other, and then substitute into your equation using the first step. So let's say it was A plus B makes C, B plus D makes E. Let me change that to be a C, so now it's an intermediate. Actually, that doesn't help me at all. Well, let me start that one over. I have A plus B, and it's going to make C. And then I have C is going to make E. Whenever, and this is my fast step, this is my slow step. My slow would come off of this, but I can't have this be my rate law. And so that's where you would go do what we just did. And again, what did we do? We assumed because it was a fast reaction, that the forward equals the reverse reaction, and then we solved for our intermediate and got what the intermediate can equal, and then we substituted it into this equation, and you can't assume that these K's are the same numbers because it's the same reaction. Scratch those out and then solve for your final answer.